Great to have you back in another lesson on heat, and kinetic theory of gases is one of the mainstream topics in physics. So what we learn in this lesson is what is Avogadro's number, what is the relationship between the number of moles N and number of molecules N, that is capital N, and Avogadro's number Na. We will also learn the ideal gas law, relate the ideal gas constant R and the Boltzmann constant K, and we learn what are isotherms and finally work on PV diagrams for various processes. Well, before we go ahead, let me request you to press the subscribe button if you've not done already, so that you continue to get notifications on all videos that are released. And if you like it, please give it a thumbs up and do share with someone who can benefit from it. So gas is nothing but a collection of atoms or molecules that fill up a container's volume, and then these particles exert pressure on the walls of the container, and this sheer speed of molecules can actually help us assign temperature to the gas in this container. So you see the microscopic properties, that is the velocity, and macroscopic property, that is the temperature, are quite closely related. Another example could be the microscopic forces that gets created when, say, a molecule of air strikes a solid surface, like say your skin, and causes atmospheric pressure, which is a macroscopic property. In fact, almost 10 to the power 32 molecules strike your body every day with an average speed of 1700 kilometers per hour to create the atmospheric pressure that you experience. Now, volume, pressure and temperature are a result of random motion of gas molecules. So the way the molecules spread themselves inside a container gives it volume, and when the molecules bounce off against the wall of the container, they create the pressure, and the kinetic energy of the particle is what defines temperature of the gas. So there are several ways we could take off on this topic, but I think a good place to start is to find the amount of gas in a sample, and Avogadro's number is what we will use to find this. Well, closely associated with Avogadro's number is the concept of mole of a gas. So what is 1 mole of a gas? So in a formal way, we say that 1 mole of a gas is the number of atoms in a 12-gram sample of carbon-12. Well, it is not a very complicated definition, but can leave us with a sense that we did not get it fully. So let us break it down in a more simple way. And a more useful question to ask is, how many atoms or molecules are there in a mole of a substance? And the answer is that there are 6.02 into 10 to the power 23 atoms or molecules, and this is Avogadro's number. So if I give you 1 mole of oxygen in a jar and ask you how many molecules are there in this jar, you should quickly say that there are 6.02 into 10 to the power 23 molecules of oxygen in it. And well, if I gave you a mole of another gas, say sulfur dioxide, the answer would be the same. So mole as a measure is quite a convenient unit to establish the number of atoms or molecules contained in a gas. So this number is called Avogadro's number, and it is named after the Italian scientist Amedeo Avogadro, and he's the one who established that all gases occupying the same volume under same conditions of temperature and pressure will contain the same number of atoms or molecules. So moving ahead, if Avogadro's number is Na is equal to 6.02 into 10 to the power 23 per mole, and I gave you 18.06 into 10 to the power 23 molecules of oxygen and asked you how many moles have I given you, you would divide the number of molecules or atoms, as the case may be, given to you by Avogadro's number to find the number of moles. Or here we would say the number of moles is equal to 18.06 into 10 to the power 23 divided by 6.02 into 10 to the power 23, which equals 3 moles. So if you're given n molecules of a gas, then the number of moles n, that is small n, is equal to capital N upon Na, which is Avogadro's number. And I'd urge you to be a little careful about the various n's appearing here, since it can get a little confusing. Well, we can also find the number of moles given to us if the mass of the sample is known. So if we are given ms grams of sample, all we need to do is divide the sample mass ms by the mass of 1 mole, often called the molar mass. So n, which is the number of moles, is equal to ms, which is the sample mass, divided by capital M, which is the molar mass. Now, if mass of one molecule is m, then the mass of Avogadro number of molecules, which is 1 mole, will be m into Na, or capital M is equal to m into Na. Then we can rewrite this equation as n is equal to ms divided by m into Na. Okay, with this background, we are set to get into understanding what is the ideal gas law. So what really we are trying to do in this chapter is to connect the macroscopic behavior of gases like pressure, volume and temperature with the microscopic properties, or how the molecule behaves in a given environment. Well, to start with, we need to figure out which gas should we take to study the behavior. Should it be oxygen, hydrogen, sulfur dioxide, or so many other gases available to us? Well, experimenters found that if you take 1 mole sample of different gases and put them in containers of similar volume and subject them to the same temperature, then the pressure the gases create would almost be the same. And if you dilute the gases or reduce the density, the difference almost disappears. So at low density or dilution, all gases obey the relationship that is PV is equal to nRT, which is the ideal gas law. And here the small p is the absolute pressure, not the gauge pressure. V is the volume of the gas, N is the number of moles of gas contained, and T is the temperature measured in Kelvin. And the symbol R is a constant referred to as the gas constant, and it is the same for all gases, and its value is 8.31 joules per mole Kelvin. So this ideal gas law is also valid for a mixture of different gases. You just need to take the total number of moles in the mixture, and you can use this formula to find any of the variables in this equation. Well, we can rewrite this equation in another form where we introduce a new constant called the Boltzmann constant K, which is nothing but K is equal to R upon Na, or the Avogadro's number. So this equals 8.31 divided by 6.02 into 10 to the power 23, which equals 1.38 into 10 to the power minus 23 joules per Kelvin. Then we can write R as equal to K into Na, or if you use this R value over here, we can write PV is equal to N into K into Na into T, or this is equal to K into N into Na into T. But we know that if you multiply Na, that is the total number of molecules in 1 mole, with the number of moles, what you get is the total number of molecules, or capital N. So we go ahead and write this equation now as PV is equal to NKT. And you can see that both equations are very useful. One connects PV and T with the number of moles present in the sample, and the other connects the variables with the total number of molecules. And needless to say, this equation also represents the ideal gas law. So if you want to write the ideal gas law in terms of number of atoms, you use the small k, and if you want to write in terms of moles, you use the big R. Well, you see, this form seems a little more convenient since you're dealing with some small numbers like R and moles instead of astronomical numbers like capital K and Avogadro's number. So you can see that using this formula, we can establish several properties of an ideal gas in a pretty simple way. Well, let me add here that there is nothing like a truly ideal gas in nature. However, if you reduce the density of real gases well enough, they would approach the ideal state. And this ideal state essentially means that under such conditions, the molecules are so well spaced out that they do not interact with one another. So this law really helps us to understand the behavior of real gases, which is the ideal gas or a very dilute gas. So let us see how this law can help us understand some real world situations. So let's take a large steel tank and fill it up with steam at a temperature of 108 degrees centigrade from one end. We then shut off the supply so that the tank is now full of steam, and then we pour a lot of water on the tank and cool it. What you'll see is that within minutes the large tank collapses and gets crushed. Now, what do you think crushed this huge tank? Well, it was the atmosphere that caused this tank to collapse, and the explanation is that as the process of cooling happened, much of the steam cooled and condensed, and since the steam condensed, the molecules N of steam in the tank and the temperature both reduced. Now we can see that the right hand side of this equation has decreased, and if the equality of this equation was to be preserved, the left hand side should also decrease. And since volume V of the tank is constant, the gas pressure P inside must fall. Now, when the pressure P falls so much that it goes well beyond the external atmospheric pressure, the outside atmospheric pressure crushes the tank. So let's move ahead and use this formula to find what is the work done by an ideal gas under various conditions. And the first one we'll examine is the work done at constant temperature. And this may sound like a repeat of the earlier chapter, but let us see if we can discover new things here. So we'll put an ideal gas in a piston cylinder setup and allow the gas to expand from an initial volume Vi to final volume Vf while we keep the temperature of the gas constant at T. And we know that such a process that happens at constant temperature is termed isothermal expansion, and the reverse is called an isothermal compression. So on a PV diagram, an isothermal curve connects points that have the same temperature, and if n moles of an ideal gas are taken and a graph plotted for it by varying pressure and volume but keeping temperature T constant, this is the graph you will get, and the equation of this graph would be P is equal to nRT into 1 upon V, or it is equal to a constant upon V. So here we have three isotherms for three different temperatures, and you can see that the value of temperature T for the isotherms increases upwards, and the reason is as follows. Well, you see the temperature of this curve should be lower than that of this curve, since if you rewrite this equation as PV is equal to nRT, you can see for the same volume the pressure here is lower, and therefore the product PV will be smaller. Hence the temperature will also be smaller since T is proportional to the product PV. So let's go ahead and see that if the path taken by an ideal gas at this temperature is say from some initial position I to final position F, then to find work done by the gas during such an isothermal expansion, we can make use of the equation W is equal to integral PdV as the volume changes from Vi to V final, and this is the general expression for calculating the work done during any process if there is a volume change. Further, we can make use of the equation PV is equal to nRT for an ideal gas and use the value of P in this equation. So let us substitute this here, and what we get is W is equal to integral nRT upon V dV, where V is changing from Vi to Vf. Now, since we are assuming this to be an isothermal expansion, T will be a constant, and we can pull this out along with R and N, which are also constants, and rewrite this equation as W is equal to nRT and the integral dV upon V, which therefore equals nRT ln of V as V changes from Vi to Vf. And then this simplifies to nRT times ln of V final minus ln Vi, or W is equal to nRT ln Vf upon Vi for ideal gas and isothermal process. What you need to remember here is that ln is a natural logarithm with base e. So you see, when expansion happens, Vf is greater than Vi and the ratio Vf upon Vi becomes greater than 1, and the natural logarithm of a number more than 1 is positive, and therefore you get positive work done by an ideal gas when the isothermal expansion happens, which is quite in line with what we learned in the last lesson. Likewise, when compression happens, Vf is less than Vi, so the quantity becomes less than 1 and natural logarithm here becomes negative, and as a consequence the work done becomes negative, which again is in line with what we have learned so far, that compression results in negative work done by the gas. And if Vf upon Vi is equal to 1, natural logarithm of 1 is 0 and you get 0 work done, which again makes sense, since if Vf upon Vi is equal to 1, Vf is equal to Vi and no volume has changed and therefore no work has been done. And you must remember that this equation is valid only for constant temperature processes and cannot be used for any other thermodynamic process. And you can see that if temperature had varied, then T here cannot be taken out as a constant as we did when we were deriving it. Well, we can always use this equation to find the work done during any process. So if volume is kept constant, you see this quantity reduces to 0 and therefore work done is 0. And if we keep pressure constant, then we can say that the work done is P into Vf minus V initial, or simply P delta V. Well, before we close this lesson, I would like to test your understanding of this lesson. And the question is, what is the work done when there is no change in volume? Put your comments below and let me see if your answers are correct. So if you like this video, go ahead and give it a thumbs up, and please do not forget to subscribe to this channel for many more interesting videos.